Hi, and welcome to Integrated Science. Today we have moved through talking about our solar system. We've talked about the formation of stars, and now we're going to kind of get into the idea of where did all of this come from. And it all has to do with stars, but we have to talk about just the idea of the Big Bang, or where did the universe come from. So at this point, we're kind of going to talk a lot about theories that associate with things that we have talked about before, such as radiation and our electromagnetic spectrum and frequency. So we're going to brush over those two tools just a little bit today. So remember, we've talked about thermodynamics. We have our three different types of thermodynamics: our conduction, our convection, and our radiation. And so today we're going to talk about that idea of radiating energy in the form of waves. And so when we have energy moving through a system, we can see that energy being dispersed throughout, and then we can get signals from that. Some of them are radio waves, some of them are X-ray and gamma rays, microwaves, all these different types of radiations. And then that leads us back to our spectrum. So if you remember our spectrum, we have our red side of the spectrum, and it goes Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, all the way to our violet section, where our different wavelengths and frequencies alternate. So remember, our red side has our long wavelength and low frequency, whereas our purple side has very short wavelengths and very high frequency. And so that's going to come into play today as we talk about where did our universe come from. We know it's there. Scientists are able to take pictures, use satellite images, and we can see other galaxies, and then within those galaxies, excuse me, and then within those galaxies we can also see stars and even sometimes other planets. So, and then we can actually even see that in our own galaxy and then within our own solar system. So today we're going to look at the notes. So if you're in Canvas, we are going to go down to the space unit, and we are going to click on the Big Bang PowerPoint. And I already have it pulled up for us here, so, well, I thought I did. Maybe I do not. Well, I will have it pulled up now. Oh, it's right here. The graphics in here are just, you guys are going to be blown away by this. All right, so, oops. Well, darn it. That's where I'm going to start. All right, so let's go ahead and get started. So I'll give you a little bit. I'm going to pull all this up here. All right. Kind of silly here. So, a timeline of the Big Bang. So the idea is that the way we can kind of figure out the age is by going back once again and thinking about how light and frequency is being traveled. We know that the sun is about 5 billion years old because of the fusion rate that is happening there. And so then we can even go further back and say, well, if this light is coming to us at this speed, what was it at 100 years ago? What was it then again at 1,000 years ago? So we kind of keep going back to that same idea. So the beginning of the universe, we are just going to start with somewhere. I don't want you to get so hung up on the idea that we need to know exactly what happened. We want to talk about it, and we want to focus on how do we know it's expanding? How do we know that it's where it is today? So I don't want you to get all hung up on like what made it bang, what made it expand, blah, blah, blah. There's lots and lots of different ideas and theories behind all of that. And that's not what I'm really worried about with this class. I'm worried once again in figuring out the speed and the distance, and how do we know that it is what it is today, and how do we know that it's going to expand even further out tomorrow and the next day and the next day. So hypothetically, we believe that the universe, or scientists believe the universe, is about 13.7 billion years old. And once again, they're able to figure that out through radiation, and I'll explain what that looks like here in a minute. So then we fast forward. So lots of things happened in this time. So for whatever reason, something exploded or something caused a trigger reaction that allowed thermodynamics to start to take place. So we had conduction, convection, and radiation, and then there was also the fundamental blocks of just physics. So the spectrum. And then we had magnetism and electricity and gravity, and all those four things were here, and they started to work together. Don't know why, they just did. And so as they did that, they started to form. If you have electricity and magnetism, then you can have that energy moving through. And so think about the law of conservation of energy, is that if you have energy, you can create matter. And in that first minute, that expansion, that's exactly what happened. That energy transferred and created some matter. And then you can look up all kinds of stuff talking about antimatter and dark energy and all kinds of different things. But just understand the idea that there was matter there. And if you have matter starting to form over time, the simplest of all elements is going to be created first, which is, we've already talked about this, hydrogen. And so that hydrogen was readily available somewhere in this timeline. And so if you have a lot of hydrogen, what do you think probably formed first? Stars. So these stars were really big, super massive, and then they got to the end of their life with fusion. And if they're supermassive stars, they're going to do one or two things. They're going to either supernova and then create a new nebula for new things to form, or it's going to create a black hole, which then allows gravity to kind of form. And we've talked a little bit about this idea that in all galaxies, at the center, there's a black hole. And that black hole is able to hold these huge structures together, just like the sun is massive and it's able to hold the solar system structure together. It's just that galaxies are on a much bigger scale, so they have black holes in the middle of them. And so that process kept happening over and over and over and over again until you get more formations of galaxies, more formation of stars. And so think 13.7 billion years, that's a really long time. We aren't even, so if we're here and then the earth is only 3, that is 10 billion years that things are happening in this time frame. So 5 billion years, we believe that our sun was created or started to fuse together hydrogen and helium. Took a couple more billion years for all that matter to kind of settle down. And then we have the earth evolving at about 3.8. And then we're here way at our modern time. So the Big Bang Theory is a theory about two different things. What the universe was like in the beginning and what happened in the universe now, or what's happening in the universe now. And that's what we're going to focus on, is what was there in the beginning and what's happening in the universe now. So here's our universe today. It's really big. And we know that it's big, and we know that things are moving outwards because of Hubble's telescope. He was Edward Hubble himself. He was able to measure the way that objects were moving, and he was able to measure that year after year after year, and he noticed that they just kept getting further and further and further away. So the red represents, well, what if we hit the rewind button? And so we know what it is today, and we know the rate that it's moving at, and it's constant. What if we just went back and rewound it? So this is the universe a million years ago, shrunk just a little bit, shrinks a little bit more, and more, and more, and more, and more, and more. So the idea is that we know the universe is expanding. So it started out actually really, really small, and then it's moved out to what we see today. And that's kind of the big thing I want you to think about and understand, is that we can see as scientists that the universe was once really small, and now we know it's really big. I think it goes down and down and down. There you go. So you get that little itty bitty, what happens there? So the universe is expanding and has always been expanding since the beginning. And that's the big key I want you to understand. Don't worry about why it banged or exploded or whatever. Just want you to know that it is expanding, and we can see that, and we can mathematically prove that it was once smaller and now it is bigger, and we can prove that today it is one size and tomorrow it's going to be the next, and then the next, and then the next. The second thing that we're going to talk about is, in the beginning, the universe was very small, hot, and dense. It had all those fundamentals in there. And once again, as the universe expands, it's also cooling down. So think about, as those particles move further and further and further away from each other, it gets less compact. And if you think about like our transfer of energy, if there's not enough particles for that energy to transfer through, it gets cooler and cooler and cooler. And that's what's happening. So like here, it was really hot, 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 warm, warmer. And then as we move further and further and further out, it gets cooler and cooler and cooler. So the universe is expanding. We can prove that. And I'll talk about why here. The universe started out small, hot and dense, and the universe is cooling as it expands. Those are our three thoughts. How do we know? That's the big question, right? What caused the Big Bang? Don't know. We might never know. That's okay. Once again, that's not what I want you to worry about. So the first way that we're going to talk about we know the universe is expanding is our Doppler effect. So remember, our Doppler is the change in motion relative to the observer. So we are the observer here on Earth. And so if we think back, remember that things that are moving away from us get that long wavelength of low frequency, and that trends to the red side of the spectrum. Whereas if we get short wavelength and high frequency, that is towards the blue or the violet side of the spectrum. So let me read this to you and we'll talk about it. So the redshift is a stretching out of straight starlight that we would see if the universe was expanding, meaning that when we look at things in space, if things are moving away from us on Earth, we normally see that long wavelength, low frequency. So we tend to see things trending to the right side of the spectrum, to the red, the orange, to the yellow side of the spectrum. Now, if something is moving towards the Earth, compacting the starlight that we would see, the universe is collapsing and condensing. We're looking at, when we talk about redshift and blue shift in relation to the universe, we are talking about galaxies. And most of the time, 99.9% of the time, when astronomers look out into space and they observe galaxies night after night after night, they are moving to the red side of the spectrum. And we call that redshift, meaning they are getting the long wavelength and low frequency. Other things are moving towards the blue, but galaxies are normally trending towards that red side. The other thing that we talked about is that radiation. And so we are actually able to hear the radiation of the universe cooling, and it's called the cosmic background radiation. And you can hear it when your TV or your radio goes out and you no longer have a connection. You'll get that shh, that fuzzy noise. That's actually static from all around the earth. It's the universe talking to you, and it's actually just heat. And so it's coming at us in what we call a microwave. Well, if we think about a microwave radiation, that is on the red side of the spectrum. That's low energy. So scientists hypothesize that when everything was really close together, the universe was probably giving off much more of a X-ray or a gamma ray or UV radiation. And now we're getting much more of a cooler end of it, a microwave. So everything that we look at in space, there is a faint layer of energy. It is nearly all the same temperature and wavelength, implying that it all comes from the same event, creating the Big Bang, and that's a cosmic background radiation. So I have a couple videos that are going to accompany this to kind of talk about that cosmic background radiation and the red and the blue shift. So please do make sure that you watch those, and we'll kind of talk and discuss about these huge ideas that we've been just going over and over the past couple of weeks with our energy unit, our wave unit, and now here it is again in our space unit. Hope this helps. I'll see you again.